Advanced composite structures and bonded materials have revolutionized modern aircraft construction. They are used in thrust reversers, engine cowlings, flight control surfaces, and other secondary structures. Composite structures are now incorporated into a greater number of aircraft used for both civilian and military applications by all of the major aerospace manufacturers. They are also used in primary structures in UAVs. For the industry to certify these structures, it is necessary to determine the strength of the adhesive bonds in these structures. Conventional non-destructive testing, NDT methods, are unable to assure that the bond strength is acceptable for service. There are a number of advantages that bonding has. In particular, composite bonded structures produce greater stiffness. It allows uniform load distributions, forms smoother aerodynamic lines and surfaces, and has the possibility of eliminating rivet holes or significantly reducing them. Bonded structures do require a reliable inspection method for characterizing the strength of composite bonds. The solution we have developed is called laser bond inspection. This represents how the process works in a simplified fashion. Laser bond inspection, or LBI, is a pulsed laser system. Depending upon the type of structure that you're inspecting, the laser parameters could be anywhere from 5 to 50 joules of laser energy and 100 to 300 nanosecond pulses. Typically, our beam diameter is around 10 millimeters. Preferably, you'd like to see the beam diameter much larger than the thickness of the bonded structure so that you get reasonably planar waves. The process works like this. You prepare the material to be inspected by applying a thin layer of material to absorb the laser beam, which could be tape or black paint. Then you flow a thin layer of water over the opaque overlay. What happens is that the laser beam comes through the transparent water overlay, is absorbed by the opaque overlay, a plasma is created and starts to blow off. The water overlay temporarily contains the plasma and intensifies the shock wave that is then produced as the plasma blows off. This directs the compressive wave to travel forward through the composite material, through the bond line, to the back free surface of the material. At that point, because of the impedance mismatch between the composite material and the air, you get a reflective tensile wave, not shown here, which comes back through and it interrogates the bond line. This graph is a simplified version of what happens in the composite material where you produce the shock wave. It describes how we form the tensile wave. Again, here's a schematic of what happens as I described before. The laser beam comes in, goes through the overlays, produces a shock wave that propagates through. Here's a one-dimensional view, a simplified view, in which the beam diameter would be much greater than the thickness of the material. You form a compressive wave, it travels through the material, and as it reaches the back surface, it begins to get reflected as a tensile wave, and so it gets canceled out as the tensile wave and compressive wave starts propagating backwards. You have a small region where there is very low stress. After it continues to propagate, it propagates outside, beyond where the compressive wave was, and you have a tensile wave then that is flowing back towards the bond line, which will stress the bond line and interrogate the bond line to test the strength of the bond line. This is a code simulation that results from a 19 millimeter diameter solid beam that is interrogating a 19 millimeter thick aluminum plate. In this particular case, since the beam diameter is about the same thickness as the aluminum plate, the stress waves that are produced are much more complicated. It's just not made up of a single compressive wave moving forward, but actually has compressive and tensile waves moving forward. The complication exists because of the edge effects on the beam finite dimensions, but this shows exactly what happens at the back surface. Shown here is the XY dimension of a particular shot in time at 3 microsecond time points after producing the shock wave. You can see here that this is a moment in time in which the main compressive is close to the back surface. What is plotted here is the rear surface velocity as a function of time. The plot shows that the main stress wave hits around a little after 3.4 microseconds, and there is the second tensile wave. Then there's a third compressive wave and a second tensile. What happens is that at this time, the compressive stress wave reflects off, comes back through, gets reflected off of this surface, comes back through again, but is attenuated in its motion through the material, and you start the period again. Now, this is a sample again of a case where the diameter of the solid beam is approximately the thickness of the aluminum plate. As you decrease the thickness of the plate, you go down to a couple of millimeters, then the edge effect that I described disappears, and you basically just have a compressive wave going forward. You do not have these additional waves. This indicates to you that by forming the shape of the beam and the energy of the beam and the pulse width of the beam, that you have some control over shaping what the compressive wave will be going through the material. This is a Boeing simulation that was provided to us. Laser bond inspection creates a stress wave that can test the strength of an adhesive interface in a composite bond. The strength of the stress wave can be selected by varying the energy and pulse width of the laser beam. The strength of the reflected tensile stress wave produced can be selected to fail weak bonds while strong bonds are unaffected. I'll describe that more when we cover how we measure bond strength. LBI can be set to detect weak bonds. It is non-destructive to strong bonds. It can also detect kissing bonds. These are bonds in which the bond line is in intimate contact with the laminate that is around it. There's no gap between the bond line and the composite material, but it doesn't have good adhesion to the surface. So there's a weakness there that would be important to detect. LBI will also detect variations in bond quality, different types of surface preparation, adhesive mixing, and if there's contaminations in the bond line material. It is a localized test of bond strength in that it's measuring the strength of the bond that is in the region of the diameter of the laser beam being used to interrogate the bonded structure. By varying the fluence of the pulsed laser beam, we can modify how we affect the bond line. If you start off at a very low fluence, which is like 3.4 joules per centimeter squared, using ultrasound after the testing, we can see that there is very little damage to the bond line. As you gradually increase the fluence level, you see more and more damage until you get to a point that you have strongly damaged the bond line. This is just one technique that we use post-test. We also have another technique that we do using an EMAT gauge, which I'll talk about later. EMAT is an electromagnetic acoustic transducer which actually measures the bond line in real time. This is an indication of how we detect a bond line failure after the fact. You can use ultrasonic measurements after the laser beam for post-examination of the test condition. Laser bond inspection can detect kissing bonds. This is an example of a visor measuring the surface velocity, the back surface velocity of a composite material. Again, we have our normal test setup with the laser beam and the overlays looking at the bond line. The beam is weak enough that it does not affect the bond line. This is an indication of the back surface velocity as a function of time. This is similar to the graph that I showed you before about the simulation. This blue indicates the case in which we have no damage and there's no kissing bond. You can see that has no damage. Then we take the composite and replace it with a composite that has a kissing bond, in which we use a release agent to weaken the adhesion of the bond line to the composite material. Then we interrogate it with the pulse laser and we measure it with the visor, and as you see, we get a very different signal. This is the indicator that you have a bond line that is a kissing bond. This is one of the key tests that LBI performs, that it can detect kissing bonds, whereas most conventional technologies are unable to pick up this type of defect. Next, we look at measurement of bond strength by laser bond inspection. In order to give bond strength a damage parameter as a sign of laser fluence, what we do is assign a value of 0 when no bond damage can be detected by the UT scan. This is what we just discussed and what UT can detect, what's there, and if there's a lot of damage or no damage. It's a very simple method of determining bond. Then, if there is perceptible bond damage, we assign a value of 1/2. And if we detect a significant level of bond damage, we assign a value of 1. Using that technique, we're able to discern variations in the strength of a bond line. This graph illustrates 3 different composite structures that have weak adhesive, a medium adhesive, and then the standard adhesive. So this is a baseline in which the standard adhesive has greater strength and the weaker bond lines go to the left. The way we do this is that we start off at a low fluence level, and if we detect no damage, we assign a value of 0. As we increase the fluence level, you can see that we start seeing some damage. Under 5, we see a little bit of damage, so we assign it a value of 1/2. And then above 6, we see a lot of damage and are damaging it consistently. It shows that around 5 gigawatts per centimeter squared, we see damage in the bond line on this sample. We continue on with the next sample, and this has a stronger bond, so it breaks at a higher fluence level. As you see, it's breaking above 10, and the standard bond line breaks above 15. Boeing did some mechanical testing on these and found that the mechanical strength broke around 50% of the bond strength of the strong bond. The middle adhesive broke about 75%. With LBI, we detected about a 43% threshold, and for the stronger bond, we detected 67%. So there's a good agreement between what laser bond inspection is telling you, what's happening, and what's happening mechanically. This graph shows you the effect that multiple shots have on a bond line. It's important to understand that if you interrogate these materials and you are doing damage to it that weakens the structure, then you're imparting damage. And so we wanted to avoid that and know how the structure behaves with multiple shots to see if indeed we are interfering with the strength of the bond line. A test sample is represented here. In this particular case, we graphed the number of pulses to failure as a function of front surface velocity. You can see at the higher velocities, that means a higher stress and higher fluence level. That's where you're doing the damage, and it only takes one shot to break the bond. But as you go to lower velocities, as you get into the region where we're doing bond detection, then you can see that it asymptotes out, that you get to a point that below which you don't see any failures even after multiple shots. So this is an indication that laser bond inspection can be used without interfering with the strength of the structure. Now we'll go on to our mobile laser bond inspection system. These are just the general specifications for that laser system. It is capable of putting out 5 to 50 joules. Pulse width can be varied between 100 and 300 nanoseconds. Both of these parameters are adjusted according to the requirements of the material you're inspecting, considering the thickness of the material and other characteristics of the material. The repetition rate is one shot every 8 seconds. We use an infrared laser beam at 1054 nanometers. The dimensions are about 6.5 feet high, 5.3 feet wide, and 13 feet long. This picture is of the original mobile system built on a United States Air Force program. It shows the main laser system. The optical configuration of the laser is in the upper chamber, and all the electronics are in the lower. We deliver the beam by an articulated arm that goes into an inspection head. This is the original inspection head we developed, and we have developed an updated one that we'll look at next, but you can see that it's a pretty compact system. It can be taken through standard double doors and be easily moved about. This is the new inspection head that we developed. You can see that it is more modular. The inspection head contains an overlay water delivery and removal system so that it picks up the water after it applies the laser beam and contains the water. The system has quick disconnects so that the water lines can be easily removed. It also has a vacuum hold down that prevents laser light from escaping so you can use it in a safe fashion. It has controls and LEDs that tell you the status of the system and if you have a good spot or a bad spot in the composite. A computer system acquires all the data and stores it in a database. The sensor that we use on LBI is an EMAT, which is like a visor. It measures the surface velocity to determine the strength of a bond line. Here's the bottom of the head, the water nozzle to deliver the overlay water, the EMAT coil used to pick up the signal of the moving surface of the composite, the water evacuation, vacuum hold downs, and the magnet for the EMAT. Now let's discuss how the EMAT works. Since we're dealing with composite materials, we need a conducting path for the EMAT. This is just a reproduction of the actual EMAT. To get that conducting path, we have developed a special tape that has a copper trace that provides the conductive path for the EMAT. The EMAT is positioned at one end of the coil, and the laser beam is positioned at the opposite end of that circuit for the conductive path. The magnetic field lines that are produced by the inspection head run parallel to the surface of the tape. The laser beam comes in, and as a result of the shock wave that is produced through the composite, that surface starts to move. As the conductive pattern moves through the magnetic field, and electrical current is set up in the path. That electrical current is sensed by the EMAT. So it is able to detect the surface velocity, the surface motion, just like a visor, and determine exactly what type of inspection and what type of variation the bond line is going through as a result of the interrogation that LBI is doing. To use the EMAT gauge, we use a technique of low-high-low inspections. It consists of 3 laser pulses. First, we apply a low-energy pulse that has absolutely no effect on the bond itself, but it gives you the condition of the bond line before you interrogate it with the strong shock wave. That is a shock wave just strong enough to affect weak bonds, but not strong enough to affect a strong bond. So we do the first interrogation with a weak laser energy pulse, and then we apply the high energy pulse that actually does the interrogation to see if a weak bond exists. Then we hit it again to determine if anything has changed as a result of hitting it with a high energy laser pulse. Finally, we compare the 2 lows. If they are the same, then the bond is good. If they are different, that indicates that there is a problem in the bond line. This purplish trace is the main shock wave that LBI produces. That's the high energy shot. And as you compare the post-trace from the final low energy shot to the trace from the pre-trace from the first low energy shot, you can see that there is a distinct variation in the two, indicating that the bond line is weak. If it was a good bond line, the difference would be a flat line. This is similar to the signal that you saw that we covered earlier with the Visar and the simulation that Boeing put together. Basically, we have a compressive wave, then the tensile, then this series of tensile and compressive waves. To summarize, laser bond inspection creates an internal tensile stress wave that tests the strength of an adhesive interface of a bonded structure. Laser bond inspection detects weak bonds at the adhesive composite interface. The strength of the stress wave is selected by varying energy and pulse width of the laser according to the requirements of the particular composite material being investigated. The strength of the reflected tensile wave is selected to fail a weak bond while strong bonds are unaffected. LBI can inspect bonded structures that are less than 1 inch thick. And our conclusion, laser bond inspection systems are now available for purchase from LSP Technologies. The mobile laser system can be implemented on a production or depot floor. The mobile system can be configured for different production requirements. And laser bond inspection of composite structures is available at LSP Technologies. If you want to test some material, we're available for testing it.